Have you ever stopped to think about what truly happens inside the sun? We're not just talking about a bright ball in the sky. We're facing a colossal thermonuclear machine, a natural reactor that burns millions of tons of matter every second, generating all the light, heat, and nearly all the energy that sustains life on Earth. But how is this possible? How can something located 150 million kilometers away be so essential? The answer lies deep within, at the sun's core, where conditions are so extreme they defy imagination. At the center of the sun, temperatures reach 15 million degrees Celsius. The pressure is billions of times greater than on Earth's surface. In this controlled inferno, hydrogen atoms are crushed together with such force that they fuse, forming helium. This process is called nuclear fusion, and it holds the secret of the sun. When two hydrogen nuclei collide and transform into helium, a small portion of the original mass vanishes. But it doesn't disappear magically. That missing mass is converted directly into pure energy, according to Einstein's famous equation, E equals mc squared. Every second, the sun converts 4 million tons of matter into energy. Yes, 4 million tons. To put this into perspective, this amount of energy could power trillions of Earth-like cities, and still leave plenty to spare. But why doesn't the sun explode? Why doesn't it consume itself instantly? Despite this immense energy output, the sun is enormous. It has over 300,000 times the mass of Earth. Even burning this staggering amount of matter per second, it has enough fuel to keep shining for another 5 billion years. Inside the sun, this energy begins its journey in the core, but it doesn't escape immediately. Between the center and the surface lie two main layers, the radiative zone and the convective zone. In the radiative zone, energy travels in the form of photons, particles of light. But the path is so dense, packed with countless particles, that each photon takes thousands, sometimes up to 1 million years, to make its way out. It's like trying to cross a crowded room, slowly being deflected, absorbed, and re-emitted thousands of times. Only then, upon reaching the convective zone, does the energy rise upward like bubbles in a pot of boiling water. This slow, turbulent motion carries heat to the surface, where finally, light is released and travels through space toward us, arriving in just 8 minutes. All of this complexity reveals a fascinating truth. The sun isn't just a star. It's a living dynamic system, governed by perfect physical laws that transform matter into light, and light into life. And the most incredible part? All of this happens in silence, without us noticing, except when we feel its warmth on our skin or see its brilliance in the sky. But there are still questions. How do we know all of this? Can we actually observe what happens at the heart of the sun? That's exactly what we'll explore in the next part. The nuclear engine, how hydrogen turns into light. At the heart of the sun, where pressure is crushing and temperatures exceed 15 million degrees, something extraordinary happens billions of times per second. Hydrogen turns into helium. And in this process, a tiny fraction of mass disappears, converted directly into energy, just as Einstein predicted. This mechanism isn't combustion or chemical explosion. It's nuclear fusion, a phenomenon so powerful it powers every star in the universe. But exactly how does it work? The sun doesn't fuse all atoms at once. It follows a step-by-step path known as the proton-proton chain, PP chain. It's an elegant, though chaotic, process where subatomic particles collide, transform, and release energy in the form of light and heat. It all begins with two protons, hydrogen nuclei. In the sun's core, they travel at incredible speeds, driven by extreme heat. When two protons collide with enough force to overcome their natural electrical repulsion, one can transform into a neutron. At that instant, two new particles are born, a positron, the antimatter counterpart of the electron, and a neutrino, which escapes immediately into space. The result of this first collision is deuterium, a nucleus made of one proton and one neutron, bound together by nuclear forces. In the next step, this deuterium nucleus collides with another proton. The fusion produces a light isotope of helium, helium-3, and releases a high-energy photon, a gamma ray. This gamma ray doesn't escape. It's absorbed by the surrounding plasma, slowly heating it, helping keep the sun shining. Now comes the final stage. Two helium-3 nuclei, formed in separate reactions, collide. The result? A stable helium-4 nucleus, made of two protons and two neutrons, and two free protons, which return to the mix to restart the cycle. But here's the key point. the total mass of helium-4 is less than the sum of the 4 initial protons. That difference, about 0.7% of the original mass, doesn't vanish. It's converted into pure energy, again through E equals mc squared. Each reaction releases a tiny amount of energy. But multiplied by quadrillions of reactions per second, the result is the continuous production of 384 sextillion watts, all the energy that lights up our solar system. It's important to understand, the sun doesn't burn fuel like a rocket or a power plant. It transforms matter into energy, on a cosmic scale. And every grain of light reaching Earth began its journey as a neutrino escaping the core or a photon trapped in a maze of plasma. This process has been running for 4.6 billion years, and will continue for another 5 billion. All because the sun has enough mass to keep this natural nuclear reactor running perfectly. But how do we know this actually happens? Can we really confirm these reactions deep inside? That's exactly the question that leads us to the next part. The sun's ghosts, the mystery of solar neutrinos. At the heart of the sun, billions of nuclear reactions happen every second. But something even more extraordinary escapes this cosmic furnace, nearly invisible particles called neutrinos. They are born at the exact moment two protons fuse in the proton-proton chain, and they shoot straight out of the solar core, unimpeded. In seconds, these neutrinos cross the sun's 700,000-kilometer radius, plasma, radiation, convection, and race into space at the speed of light. Here on Earth, 60 billion neutrinos pass through every square centimeter of your body each second. They fly through you, your home, the entire planet, as if nothing were there. They don't interact with atoms, 'cause no harm, leave no trace. They're like phantoms of the universe. And yet, that's precisely what makes them so special. While sunlight takes millions of years to reach us, neutrinos bring real-time information from the sun's core. They are the only direct proof that nuclear fusion is truly happening deep inside. The problem? For decades, scientists could only detect 1/3 of the neutrinos predicted by theory. It was as if 2 out of every 3 ghosts had simply vanished. This became one of the greatest puzzles in solar physics, the solar neutrino problem. Since the 1960s, experiments like Ray Davis's, deep inside a gold mine in the US, tried to capture these particles using massive tanks of liquid chlorine. The idea was that very rarely, a neutrino could interact with a chlorine atom and turn it into argon, a detectable event. But the results were always the same. Only 1/3 of the expected neutrinos appeared. Were the sun's models wrong? Was nuclear fusion not working as we thought? Or was there something fundamental we didn't understand about neutrinos themselves? For years, the scientific community debated this mystery. Some believed the sun might be going through a low-activity phase. Others suspected flaws in the detectors. But the more refined the instruments became, the more persistent the deficit remained. Then came a revolutionary hypothesis: neutrinos change identity during their journey. We now know there are 3 types or flavors of neutrinos: electron neutrino, muon neutrino, tau neutrino. Old detectors could only see the electron neutrino, the type directly produced in the sun's core. But what if, during their trip through space, these neutrinos oscillated between the 3 types? If true, then the missing 2/3 hadn't disappeared. They had simply changed form, becoming invisible to earlier detectors. It was a radical idea. And it required a profound shift in particle physics, because only particles with mass can oscillate. Until then, neutrinos were believed to have 0 mass, like photons. Accepting oscillation meant accepting that neutrinos have mass, however tiny. A small change in theory, with enormous consequences. To test this, scientists needed a detector capable of seeing all 3 flavors. And here comes the next chapter, a machine buried 2 kilometers underground in Canada, ready to uncover the sun's final secret. The underground detective: how an experiment deep in a mine proved what happens inside the sun. Imagine a laboratory hidden 2 kilometers below Earth's surface, deep inside a nickel mine in Canada. There, in complete isolation, surrounded by solid rock and shielded from cosmic noise, sits a giant spherical tank, the size of a house, filled with a special liquid, heavy water. This is the Sudbury Neutrino Observatory, SNO, one of the most important scientific experiments of the 21st century. And its goal was bold: to prove once and for all that the sun shines through nuclear fusion. Since the 1960s, scientists have been trying to detect the neutrinos born in the sun's core. But there was a problem. Every detector recorded only 1/3 of the expected number. Were the models wrong? Was the sun changing? Or was something missing in physics itself? The answer lay within the neutrinos, not because they disappeared. They were changing their identity. We now know there are 3 types of neutrinos: electron neutrino, muon neutrino, tau neutrino. Old detectors could only see the electron neutrino, the type directly produced in the proton-proton chain inside the sun. But if, during their journey to Earth, these neutrinos oscillated between the 3 types, then the other 2/3 would simply go unnoticed, invisible to the instruments of the time. This hypothesis required a radical shift in physics. Neutrinos can only oscillate if they have mass. Until then, it was believed they were massless, like photons. Accepting oscillation meant accepting that the standard model of particle physics needed revision. To test this, scientists needed a detector capable of seeing all 3 neutrino types at once. And that's exactly what SNO was designed to do. The secret was heavy water, water where hydrogen atoms are replaced by deuterium, a heavier isotope. When a neutrino interacts with a deuterium nucleus, it triggers different reactions depending on its type. If it's an electron neutrino, it splits deuterium into a proton plus neutron. If it's a muon or tau neutrino, it can scatter a free electron, producing detectable light. With this technology, SNO could measure not just electron neutrinos, but also the total sum of all 3 types. And the result was clear, direct, and revolutionary. The total number of detected neutrinos, combining all 3 types, matched the solar model predictions perfectly. The neutrinos had never vanished. They had simply changed form along the way. This discovery, announced in 2001, was a landmark in science. For the first time, we had direct proof that nuclear fusion occurs in the sun's core. But the impact was even greater. We proved that neutrinos have mass, even if tiny. A discovery that forced fundamental revisions in modern physics. SNO didn't just confirm how the sun works, it opened a new window to the universe, neutrino astronomy. Now we can see extreme cosmic events, like supernovae and neutron star collisions, through these ghostly particles. And it all began with a simple question. Why do we only see 1/3 of the neutrinos? The answer came from the depths of a mine, where men and women, in silence, listened to the whispers of the sun. In the next part, we'll explore how this energy directly affects life on Earth, and why nearly every form of energy we use ultimately comes from the sun. All energy comes from the sun, the secret behind life on Earth. When you turn on a light, take a hot shower, fill your car with gasoline, or simply eat a piece of fruit, you might not realize it, but you're using solar energy. Yes, all this energy, directly or indirectly, comes from the sun. The sun isn't just a distant star in the sky. It's the primary source of nearly all energy on Earth. Without it, there would be no weather, no seasons, no photosynthesis, no food, no oxygen. Life, as we know it, simply wouldn't exist. But let's go deeper. Almost every form of energy we use is ultimately derived from the sun. Think about hydroelectric power. It comes from water falling into dams, turning turbines that generate electricity. But where does the water come from? From the water cycle, ocean evaporation, cloud formation, rain filling rivers. And what powers this cycle? Sunlight and solar heat. Without the sun heating the oceans, there would be no evaporation, no rain, no rivers. So even hydropower is disguised solar energy. What about wind energy? Winds are caused by temperature differences in the atmosphere. Warm air rises, cold air sinks. These thermal differences are created by the uneven heating of Earth's surface by the sun. So even wind turbines run thanks to the sun. And biomass? When you eat a banana, you're consuming energy stored by the plant through photosynthesis, a process that converts sunlight into chemical energy. Even ethanol from sugarcane is solar energy transformed into fuel. And oil? It seems unrelated to the sun, but it's not. Oil formed millions of years ago from remains of marine organisms and plants that lived thanks to sunlight. The energy they stored became fossilized, now extracted as fossil fuel. In other words, gasoline, diesel, natural gas, all of it is solar energy stored for millions of years. Even your own body depends on the sun. Every movement, every heartbeat, every thought is powered by energy that began as sunlight captured by plants, passed through animals, and reached you through the food chain. It's astonishing to realize that except for two main sources, All energy on Earth originates from the sun. The exceptions? Geothermal energy comes from Earth's internal heat, generated by natural radioactivity and planetary formation remnants. Nuclear energy, fission obtained by splitting heavy atoms like uranium, without involving the sun. But even these are minor players in the planet's overall energy balance. So the sun is far more than a bright star. It's a cosmic life support machine, a giant reactor that powers entire ecosystems, climates, and civilizations. And yet, we harness only a tiny fraction of the energy it emits. Every second, the sun releases 384 sextillion watts into space. Only a small portion reaches Earth, but even so, in 1 hour, the amount of solar energy hitting our planet is enough to power all of humanity for an entire year. If we could efficiently capture this energy, we could solve the energy and climate crises once and for all. But the deepest truth here isn't physics or technology. It's humility. We are living beings sustained by a distant star, connected to it through billions of nuclear reactions happening silently in the core of a plasma sphere 150 million kilometers away. The sun doesn't just illuminate us. It creates us, feeds us, keeps us alive. In the next part, we'll explore one of the greatest mysteries of modern physics. How did we manage to look directly into the sun's core? Using particles that travel through the universe like ghosts? Looking inside the sun, the only direct window into the stellar core. If someone asked you how we know what happens at the center of the sun, you might answer, through science, mathematical models, and nuclear physics. And you'd be right. But there's an even more astonishing answer, through particles that leave the sun in seconds, while light takes millions of years to escape. These particles are solar neutrinos, and they represent something unique in science, the only direct way to observe the heart of a star. While photons, light particles, can take up to 1 million years to cross the sun's dense layers, being absorbed, re-emitted, and deflected countless times, neutrinos are born in the core and shoot straight out in a straight line, without interaction, within seconds. It's as if they were silent messengers, sent directly from the sun's nuclear furnace, bringing fresh, real-time information about what's happening inside. When we detect a solar neutrino here on Earth, we're seeing a reaction that occurred in the sun's core just 8 minutes ago, the time it took to travel to us. That's extraordinary. It's like having an invisible camera pointed directly at the center of the sun. But why is this so important? Because all models explaining the structure and evolution of stars rely on one fundamental assumption, that the sun shines through nuclear fusion of hydrogen into helium. If this process isn't happening, or is happening differently, then stellar astrophysics would need to be completely revised. Neutrinos are the definitive proof that this mechanism is active. Each detected neutrino is a witness that, at this very moment, billions of proton-proton reactions are occurring in the sun's core. That hydrogen atoms are fusing, converting mass into energy, sustaining life on Earth. And that's exactly why the Sudbury Neutrino Observatory, SNO, was so revolutionary. It confirmed that the models were correct. But before that, there were decades of doubt. For a long time, detectors could only see 1/3 of the predicted neutrinos. Were the calculations wrong? Was the sun changing? Or was there something we didn't understand about the particles themselves? The answer came with the discovery of neutrino oscillation. These particles can change flavor during their journey, from electron neutrino to muon or tau neutrino. And only particles with mass can oscillate. In other words, by solving the mystery of solar neutrinos, we not only proved that the sun runs on nuclear fusion, we also discovered that neutrinos have mass, however tiny. It was a profound shift in particle physics. Today, thanks to modern detectors, we can not only confirm the sun's operation but also monitor its core in real time. We can observe subtle variations in neutrino production, study solar cycles, and even investigate whether the sun has gone through different phases of activity. Moreover, neutrinos have opened a new field of astronomy, neutrino astronomy. We've already detected neutrinos from supernovae, like SN 1987A, and we hope one day to capture neutrinos from neutron star collisions or even from the Big Bang itself. But the most astonishing thing is remembering that, every second trillions of neutrinos pass through your body, coming from the sun, from deep space, from natural reactions on Earth. You don't feel them. You don't see them. But they're there. And each one carries a story, of the sun that keeps us alive, of a universe pulsing in silence, and of science that, through patience and brilliance, has learned to listen to the whispers of the cosmos. In the next part, We'll explore how all this energy generated in the sun directly affects Earth, not just physically, but in every aspect of our existence, including climate, seasons, and modern technology. The sun and life on Earth, how a distant star influences everything. The sun is 150 million kilometers away, but its influence over Earth is absolute. It doesn't just illuminate our days, it regulates our time, shapes our climate, sustains our biology, and even affects modern technology. Every morning, when the sun rises on the horizon, we're witnessing much more than an optical phenomenon. We're seeing the activation of a massive cosmic system, where billions of nuclear reactions happening silently in the sun's core send waves of energy that touch every aspect of our existence. Sunlight is the foundation of the daily cycle and the seasons. Earth's axial tilt combined with its orbit around the sun creates the climatic variations we know: spring, summer, autumn, and winter. Without this dynamic, there would be no seasonal changes, no animal migrations, no planned harvests. The rhythm of life on Earth is synchronized with the sun's movements. But it goes deeper. The sun is the engine of global weather. It heats Earth's surface unevenly, more intensely at the equator, less at the poles. This temperature difference generates air currents, winds, cold and warm fronts, cloud formation, and precipitation patterns. Oceans absorb heat, store energy, and redistribute it across the planet through ocean currents like the Gulf Stream. All of this is powered by solar radiation. Without the sun, there would be no rain, rivers, wind, or climate at all. It would be a frozen world, without atmospheric dynamics, without life. And speaking of life, photosynthesis is the greatest biological miracle driven by the sun. Plants, algae, and cyanobacteria convert sunlight into chemical energy, releasing oxygen as a byproduct. This process transformed Earth's atmosphere billions of years ago, enabling the rise of aerobic organisms, including us. Every oxygen atom we breathe was released by a plant or microorganism under sunlight. Every calorie we consume comes directly or indirectly from energy stored through photosynthesis. Even wood, paper, and cotton fabric are solar products. But the sun doesn't act only gently. It also has a powerful unstable side: solar activity. The sun isn't a static star. It pulses, breathes, explodes. It has sunspots, X-ray flares, and coronal mass ejections, CMEs, massive jets of plasma hurled into space at millions of kilometers per hour. When these eruptions point toward Earth, they can cause geomagnetic storms. They distort Earth's magnetic field, disrupt satellites, power grids, GPS systems, and communications. In 1859, the famous Carrington event caused sparks in telegraph lines and auroras visible as far as Hawaii. Today, such an event could knock out global power grids for weeks. Yet Earth's magnetic field and atmosphere shield us from most of these impacts. And the beautiful northern and southern lights? They are precisely the result of this interaction. Solar particles colliding with high-altitude gases, creating colorful curtains of light in polar skies. Moreover, solar energy is becoming a practical solution to the energy crisis. Photovoltaic panels convert light into electricity, solar heaters capture heat, and future projects envision space-based power stations collecting energy 24/7, free from clouds. So the sun is not just a star in the sky. It's an invisible, constant, vital partner. It's the reason we wake up, grow food, breathe, and live. In the next part, we'll explore one of science's greatest paradoxes. How can we predict what will happen to the sun in the future, even though we've never seen its end? The future of the sun, the cosmic fate of our star. When we look at the sun, it's easy to think of it as eternal. It was born before us, shines every day, and seems unshakable. But like everything in the universe, the sun has a life cycle. It was born, it's now in its prime, and one day inevitably it will die. And this cosmic process is already written into the laws of stellar physics. Right now, the sun is in what's called the main sequence, a stable phase where it fuses hydrogen into helium in its core. This phase lasts about 10 billion years. 4.6 billion have already passed since its birth. That means we're roughly halfway through its active life as a star. But what happens when its fuel begins to run out? In about 5 billion years, most of the hydrogen in the core will be converted into helium. With that, fusion in the center slows down. Without the outward pressure from nuclear reactions, gravity takes over, causing the core to contract. This collapse generates intense heat, so much that the compressed heat ignites hydrogen fusion not in the core, but in a shell around it, like a layer surrounding the sun's heart. With this new energy source, the sun reacts dramatically. Its outer layers begin to expand. The sun grows, and grows immensely. It becomes a red giant. In this phase, the sun could expand up to 250 times its current size, engulfing Mercury, Venus, and likely Earth itself. Our planet will be vaporized, its rocks melted, its oceans boiled away. Only a glowing ember will remain, orbiting within the sun's extended atmosphere. Yet even in this massive state, it won't last forever. Over hundreds of millions of years, the red giant steadily loses mass. Violent stellar winds eject its outer layers into space, forming a planetary nebula, a luminous, colorful, expanding cloud of ionized gas. At the center of this nebula lies the sun's remaining core, a dense, extremely hot object with no active fusion. It's a white dwarf. Small, about the size of Earth, but with incredible density. A cup of coffee made from white dwarf material would weigh tons. It produces no new energy. It only slowly radiates away its residual heat over billions of years. Over time, it cools. Its glow fades. And eventually, after trillions of years, it becomes a black dwarf, a cold, dark, invisible body drifting through the void of space. It's the silent end of our star. But here's the fascinating part. Even after dying, the sun continues to contribute to the universe. The gases ejected during the planetary nebula phase are rich in elements like carbon, oxygen, and nitrogen, essential building blocks for new stars, planets, and even life. We are made of these atoms. Every carbon atom in our bodies, every DNA molecule, every drop of water, was forged inside ancient stars. In its final act, the sun will do the same, scattering its elements across space, seeding the raw material for future generations of stars and worlds. There's a tragic beauty in this. The sun doesn't just sustain life while shining, it also ensures the matter we're made of continues its cosmic journey, long after it has gone dark. But still, questions remain. Can we really predict the sun's fate with certainty? How do we know this is its destiny? The answer lies in the stars around us. Looking into the sky, we see thousands of stars at different stages of life. Some young, blue, and intense. Others, red and gigantic. Many surrounded by nebulae. And others, small and bright, like steady points in space, the white dwarfs. By studying these stars, astronomers have reconstructed stellar evolution. And since the sun is a typical medium-mass star, its fate is well understood. There will be no explosion. No supernova. The sun is too small for that. Its end will be calm, slow, majestic. But inevitable. In the next part, we'll explore one of the greatest paradoxes of modern science. How can we observe the sun's interior directly, without ever having been there? How we look inside the sun, the miracle of solar science. It's a question that sounds impossible. How can we know what happens at the sun's core if we've never been there? We haven't sent probes into its nucleus. We don't have telescopes that can see through billions of tons of plasma. And yet we know with high precision. The temperature is 15 million degrees, pressure is immense, hydrogen fuses into helium, and 4 million tons of mass turn into energy every second. How is this possible? The answer isn't in technology, but in science, the combination of theory, mathematics, experimentation, and indirect detection. It's as if the universe sends us clues, and we've learned how to decode them. The first step was understanding the laws of physics. In the 20th century, scientists like Arthur Eddington already imagined the sun might run on nuclear fusion. But it was just a hypothesis. Proof was missing. Then came the Standard Solar Model, a mathematical simulation based on equations of gravity, thermodynamics, and nuclear physics. This model predicts what the sun must be like inside: density, temperature, pressure, energy flow. It works like an invisible map of the solar interior. But a map needs confirmation. That's where the great challenge began, finding something that escapes the sun's core in real time, something fast, unimpeded, carrying a direct message from deep within. And that something exists: solar neutrinos. While light takes millions of years to escape the sun, neutrinos leave in seconds. They are silent messengers, nearly intangible, traveling through space without being blocked. When they reach Earth, they carry the signature of the nuclear reactions happening in the star's heart. Detecting them, however, was a monumental challenge. For decades, experiments like Ray Davis's detected only 1/3 of the expected neutrinos. Were the models wrong? Was the sun changing? No. The truth was even deeper. Neutrinos change identity during their journey. Detectors could only see the electron type, while the other two, muon and tau, passed unnoticed. The solution came with the Sudbury Neutrino Observatory, SNO, in Canada. Using heavy water and advanced technology, SNO could detect all three types of neutrinos. And the result was clear. The total number matched the solar model's predictions perfectly. It was the definitive proof. The sun shines by nuclear fusion. This moment marked a historic achievement. For the first time, we looked directly into the core of a star, without a telescope, without a spacecraft, without touching anything, only through intelligence, patience, and science. But it doesn't end there. Beyond neutrinos, there's another way to study the sun's interior: solar seismology. Just as seismologists use earthquakes to study Earth's interior, astronomers use sound waves traveling inside the sun. These waves are generated by turbulence in the convective zone and reflect off different layers, revealing internal density, motion, and structure. By analyzing these oscillations, called helioseismology, scientists can create detailed images of the solar interior, like a cosmic ultrasound. Combining neutrinos, mathematical models, and helioseismology, we now have an incredibly accurate picture of what happens inside the sun. It's a triumph of reason. It's a powerful example of how humanity can understand the cosmos using only mind, math, and curiosity. In the next part, we'll conclude this documentary with a deep reflection. Why does all of this matter to us, human beings, here on Earth? Why it all matters: the sun and humanity's place in the cosmos. Sometimes, we see the sun only as a daily presence. It rises, lights up the day, warms the earth, and then sets. Simple. But now, after everything we've seen, from nuclear reactions in its core to ghostly neutrinos passing silently through our bodies, this star is no longer just an object in the sky. It is our origin, our sustenance, our destiny. The sun isn't out there. It's within us. Every carbon atom in our cells, every DNA molecule, every drop of blood was forged by processes initiated inside the star, or in ancient stars that died long before Earth existed. We are made of the same matter that fuels the sun. We are children of the same reactions happening 150 million kilometers away. But the deepest truth isn't physics. It's meaning. We know the sun has an end. In 5 billion years, it will expand, swallow planets, and turn into a white dwarf. Earth will likely vanish. Life, as we know it, will cease. And yet, here we are, conscious, capable of looking up and asking, how does this work? Where did we come from? Where are we going? No other species on this planet does this. No other living being seeks to understand the universe. And in this lies our greatness. Not because we dominate Earth, but because we have used intelligence, mathematics, and curiosity to read the mind of the cosmos. Through neutrinos, mathematical models, and helioseismology, we've managed to see inside a star without ever traveling there. We've deciphered a code written in radiation, gravity, and ghost particles. And in doing so, we've proven that the human mind can transcend physical limits, reaching places beyond touch. This isn't just science. It's cosmic poetry. The sun teaches us humility. It is immense, powerful, indifferent. It doesn't exist for us. And yet, because of it, we exist. It also teaches us urgency. We know time is finite, not just for us, but for the sun itself. And while it shines, we have a unique opportunity to learn, discover, evolve. Every discovery about the sun isn't just about one star. It's about all stars, all worlds, all possibilities of life in the universe. And perhaps one day, when we look at distant stars, we'll recognize the same process. And know with certainty that somewhere far away someone, maybe like us, is gazing at their own star, trying to unravel the mystery. Because this is the sun's legacy. It gives us not only light and heat. It gives us questions. And in questions lies the beginning of every journey. This documentary doesn't end with answers. It ends with wonder. Wonder for the sun. For science. For this small blue sphere floating in the vastness, where for a brief cosmic moment, conscious beings arose to say, "We are here. We are watching. And we want to understand." Thank you for joining this journey. If this video moved you, share it. Subscribe. Because the universe is vast, mysterious, and still has so much more to reveal. Until the next time you look up at the sky.